batteries and rare earth magnets in particular. So our RELIB project is the UK's biggest project on EV battery recycling. We've also got really significant work on magnet recycling. We've got spin-out companies. So there are main areas of focus, but we are interested more broadly in the critical materials piece. But you'll see a little bit of the focus comes through in terms of, batteries and magnets in this presentation. And so in terms of the EU critical materials list, there's some key focal points here in terms of, the blue rings for battery materials, platinum group metals used in electrolyzers. So we're going to talk about that in relation to Russia. We're going to talk about rare earth magnets as well. So this was a really nice graphic from the EU that looked at 9 different really key technology sectors to the EU that they thought were going to be important in the future. And understandably, as we're going through this massive energy transition, and at the moment, the need for that is more apparent than ever. I think the climate emergency has been really visible in the UK the past couple of days. We've recorded some of our hottest temperatures ever. We've been suffering from wildfires breaking out all over London, things that we don't tend to experience in our climate. And so there's a necessary focus on energy technologies for the future in terms of batteries, the hydrogen transition, the move to electric drives in terms of traction, the move to different renewable technologies in terms of generation, in terms of wind and PV. And then, of course, there are sort of other technologies of the future that perhaps we're not going to focus on so much in this presentation, but that are considered key technology sectors by the EU in terms of robots, drones, 3D printing and ICT we will touch on. But one of our main focal points is automotive applications. We live in Birmingham in the UK, in the West Midlands. It was traditionally the home of the UK automotive industry. And so that partly explains our reason why we're very focused on critical materials for automotive applications. And when you look at sort of future vehicles, it's not just about the drivetrains where we're going to need vast quantities of critical materials for the batteries and the magnets. Did someone have a question? Oh, sorry, just to come. So yeah, it's not just about the batteries and the magnets for the drive motors, but we see with the electrification of vehicles, we're just seeing an enormous increase in the critical materials content throughout electric vehicles. And in terms of the sort of increase in demand, this is a graphic from the International Energy Agency, and they forecast enormous growth in lithium, which will be used across all lithium-ion batteries, which are seen as being a real sort of dominant energy storage technology. Graphite, which is used in the anode of lithium-ion batteries, a real significant increase in demand for graphite. Cobalt, which we're going to talk about in more detail a little bit later on, significant for Russia, although the main producer is the DRC. Lots of challenges around the cobalt supply chain, and cobalt is essential for those higher energy density batteries. Nickel, which is a very big one for Russia, given the presence of Nornickel, a big nickel refinery. We're going to look at that later. And rare earths, which although Russia isn't currently a big producer of, there are certainly reserves and potential there. So let's just take a bit of a look at rare earths first of all. 17 rare earth elements. One of the challenges with rare earth production is what they call the balance problem. So quite often these elements are sort of mined from the ground together, and then there's the challenge of separation, and then they go into a range of different rare earth applications. And what we need to do is to try as far as possible to look at that balance between the supply from different mined deposits and the demand in the end. And if we look at the sort of different applications for rare earth magnets, we can see that there's a whole bunch of different categories where rare earths are used in different applications. By volume, Permanent magnets are one of the most significant applications of rare earth, and by value, as you can see here, you know, rare earth magnets really dominate in terms of the value from you know, applications for rare earths. And so that really explains our focus at the University of Birmingham. And so we've been developing technologies to try and recycle and keep rare earth magnets in a circular economy, because we think it's going to be really important to diversify supply. The other key magnetic material for the future is samarium and cobalt. It's a less powerful magnet than the rare earth magnetic material, but it contains cobalt, which is problematic as well, but it may find specialist application in some extreme high temperature applications, for example, around electric aviation, for example. And one of the things that we can see is that beyond 2020, with the electrification of a whole range of sectors and the growth of high technology, demand for rare earth materials is expected to grow by quite some margin. And we can see here a range of different applications for rare earth materials. And from our point of view, we're looking at these different applications, and we're looking at the life cycle of these magnets in use, and we're trying to look at, out of these applications, which devices are going to come to the end of life first, and how can we develop approaches to recovering that material to try and mitigate against some of these challenges of rare earth supply. And if we look, you know, offshore wind, which is a big thing for the UK, but increasingly around the world, there's around 0.5 tonne of neodymium iron boron magnets per megawatt of wind turbine capacity. And so, you know, there's going to be a real significant demand as we look towards decarbonising. And when we break down, for example, an EV drive motor used in an electric vehicle, we can see that the bulk of the value is in the magnet as opposed to the other components. And the challenge with rare earth magnets is the sort of what's the word I'm looking for? Sorry, the volatility in the price of rare earth material. And part of the challenge around this is that China holds such a dominant position in the supply of rare earth magnet material at the moment. And I think that the tensions in Russia and Ukraine could possibly serve to even reinforce that position, as I'm going to go on to explain. And so we've seen China try and use its position around the control of export and price of rare earth magnetic material to really try and acquire more supply chain capabilities and move its way up the supply chain. So obviously China has had a very calculated policy in terms of rare earth, in terms of critical materials, and it doesn't want to be an exporter of raw materials for other people to add the value. It wants to try and add that value itself. And so we've seen the control of export and the control of the price of rare earth magnet material used to try and leverage production capacity, not just for the material, not just for the magnets, but for the finished product, to increasingly move that into China. And we saw that when they introduced export quotas, there was a massive spike in the price. There was a whole court case with the World Trade Organization. The price calmed down for some time, and we've seen more recently that price start to rise again. And if we look at the sort of environmental impacts, the way that China produces rare earth materials is you know, it's not best practice in terms of environmental standards. If we look at satellite images from Bayan Obo, these tailing ponds that you can see in the pictures, you know, they're an absolutely enormous scar on the landscape where rare earth material is leached from the landscape, processed, and, you know, nasty processes, little care for the environment, and massive environmental damage. And we can see that at the moment, China dominates where that material is mined, although there are some alternative sources. There's Mount Weld in the in Australia, and there's also a mine in the US as well. We've heard increasingly that rare earth materials coming from Myanmar, and is starting to make its way into the supply chain. So once the material is mined, there's cracking and solvent extraction, followed by electro-refining and then alloy production. And as you can see, the bulk of the alloy production and the bulk of the magnet production is located in China. And then of course that finds its way into finished components. And there was a quote from one of the previous Chinese premiers that said, that they are aware that in the past, it's been about oil and hydrocarbons, but that rare earths are, China's oil, if you like, for the future, because they can see these applications and in the future and the massive growth of those applications. And so we've seen the use of rare earths as leverage in trade disputes, with the US imposing tariffs on Chinese rare earths. The National Defence Authorisation Act was prohibiting the sourcing of rare earth magnets from China, Russia, North Korea and Iran, and in some respects maybe that legislation was to try and restart that domestic supply chain for those materials. And so the sort of counter from China was to impose tariffs on US rare earth products. So the US removed the tariffs on Chinese rare earths, and this sort of cat and mouse game continues there. But what does this mean for Russia? Well, there are non-Chinese producers of rare earth magnets. So Lynas, the second biggest producer, they take the rare earth material from Mount Weld in Australia. They export that to Malaysia for solvent extraction. And Lynas also have plans to build that capacity in the US. And there's also MP Materials that's building that whole vertically integrated value chain in the US. There are some other producers of rare earth magnets around the world. However, the Chinese position on the dominance of the supply chain gives them an awful amount of leverage. But if we look at reserves and if we look at the potential, not what's being extracted at the moment, but if we look at where these resources are distributed, Russia held the fourth largest reserves of rare earth minerals in the world. So that is really significant, and in a time when we are scrabbling for critical materials and where we are struggling to develop the supply chains, it represents to some degree a potential missed opportunity as the world needs access to these materials. And so at the moment, it's not a big producer of these materials, but it has the reserves. And Russia's articulated the ambition to become a bigger producer of rare earth materials, but at the moment it doesn't have the technology, the supply chain and the means to valorize that material that is held in the ground. But we can only wonder about how things will change in the future in terms of geopolitical tensions, but the material is there in the ground. And it may be that Russia's alignment with China, who perhaps haven't taken a stand on the war in Ukraine, means that in time China may be a beneficiary of Russian rare earths, and that may reinforce their dominance further, which is of course a concern for the West. Now, moving on to Russia and battery materials, a number of people have observed the challenges around some of the critical materials for EV batteries that come from Russia, and how the war in Ukraine may potentially impact our transition and pivot to EVs. So let's just have a little overview in terms of the demand for EV batteries first of all. So we've seen the lithium-ion battery sort of sphere in terms of technology has really taken off. Patents and papers in this area for lithium-ion batteries have taken off massively, and the demand by application for lithium-ion batteries is growing inexorably. And we see the bulk of that demand being driven by passenger vehicles. And so, there's when we look at demand, we have batteries of all different sizes and scales in a whole range of applications, all the way from very small batteries in mobile phones and portable electronics, all the way up to enormous batteries such as the Hornsdale Reserve in Australia, an enormous grid battery built by Tesla with an enormous volume of stored energy. But passenger EVs are really that point at which large batteries meet large demand. And so we also see other demand in commercial EVs. There's going to be demand in the future from stationary storage as we try and make our grid adapt to the increased penetration of more flexible generators and consumer electronics. You know, whilst there's a lot of consumer electronics in the world, the batteries tend to be fairly small. So in terms of future demand, you know, that is not significant compared to some of those other sectors. And in terms of where that demand is going to come from, obviously China has a massive domestic market for electric vehicles and it's servicing that market itself. United States, obviously a really key market as well. And then, you know, Europe in terms of Germany, France and the rest of Europe and the UK. That's the sort of distribution in terms of growth. And we see in the UK at the moment a real pivot in terms of vehicle registrations. So although in sort of market share terms, we still have some road to make up in terms of sales of battery electric vehicles compared to internal combustion engine vehicles, we can see a real change in the year-on-year sales of vehicles. Diesel vehicles especially starting to fall off a cliff, petrol vehicle sales year-on-year decreasing, but massive increase in battery electric vehicle sales and hybrid electric vehicle sales. And I think, you know, the UK is a relatively mature market in terms of electric vehicles, but we can look to other countries like Norway that are real front runner countries to see, you know, the writing on the wall in terms of this EV transition. And in the UK, the government has said that there'll be no internal combustion engine sales beyond 2030. And so that's acted as a real sort of catalyst for industry to change. And in terms of the sort of risks of where these batteries are being made around the world, Benchmark Mineral Intelligence have been tracking the growth of gigafactories around the world. And again, you know, there's a real challenge in that China have cornered the market. They've got real first mover advantage in terms of the development of gigafactories. So, you know, Benchmark have been tracking projects that are under construction around the world. And this graphic in the bottom right corner shows how that has grown over time, but the bulk of those gigafactories are located in China. And from a UK perspective, the Faraday Institution project that they formally projected that we were going to need around 6 gigafactories, 6 or 7 by 2040. They've actually revised this graph, is a little bit out of date. So in the past couple of weeks, they have published an update to say, I think it was 10 in the most recent update by 2040. So from our UK domestic perspective, that's a great demand for batteries, but we need to look at where the materials are going to come from. And so if we break down, so this is a breakdown of the General Motors bulk vehicle. And if you break down the cost of the vehicle, you can see that actually a lot of that value is located in the battery pack. And then if you look at where the value is distributed through that battery pack, you can see that actually the bulk of the value is concentrated in the cells that are within the battery, 75%. And then if you then break down the value distribution of the cell, you can see that the cathode material is where 30%, the lion's share of the value is within that cell. And so thinking about the materials, where they come from and the value added is going to be significant in terms of the value for future electric vehicles. Now, we talk about lithium-ion batteries, but there are a whole range of different cathode chemistries that fall under that umbrella. And depending on the different chemistry, there are different properties. So there are batteries which are incredibly high energy density, and then there are others that are perhaps, you know, they don't have the high energy density, but they have other favourable attributes in terms of safety or in terms of cost. Now, looking at this range of batteries in the top diagram, LCO batteries, they tend to be used in portable electronic devices where space and weight is at a real premium because they are very high energy density batteries. It's an older technology that is reliant on a high proportion of cobalt. In electric vehicles, if you were to ask someone about 3 or 4 years ago what cathode chemistries would be used in future EVs, they would have probably said that it would be between NCA, which Tesla have been using, NMC, which other people in the industry have been using. And these are batteries that still contain relatively high proportions of nickel and cobalt, which from the Russia perspective is significant because Russia are a big producer of nickel, and although not a big producer because it's dominated by the DRC, they're still a significant producer of cobalt. And for NMC batteries, they have been on a journey to try and reduce the proportion of cobalt in the battery and increase the proportion of nickel over time. So we've seen this sort of evolution from the sort of first generation batteries, NMC 111, and there's been plans to take that to 622, 811, and people even now talk about 9.5.5. And with each step, you are increasing the nickel content of the battery and decreasing the cobalt content of the battery. Now, more recently, there has been a little bit of a pivot. So on the right hand side of the LNO batteries that we used in some of the first generation Nissan Leaf cars that were really popular in the UK. I don't know so much about the US, but of particular interest is LFP batteries. Now, people refer to these, somewhat jokingly as rust and fertilizer batteries. So lithium ferrophosphate batteries contain iron and phosphorus, and so they don't have the critical material content of the nickel and the cobalt. So that's significant when we're thinking about the evolution of the market and the different materials that are going to be required to power the battery revolution. But they do still require phosphate for their production, and again we'll look at that in a second in the Russian context. Now, to try and think what the demand might look like for future materials, we need to have some sort of view on what the future cathode mix might look like. And this graph on the left hand side, this came from the Faraday Institution, our sort of UK body that's looking at trying to catalyse the battery industry. And as I say, if you asked people a while ago what batteries were going to dominate the market, they would have said the higher power NCA and NMC batteries, because the sort of prevailing presumption was that people were really going to favour range and that they would be wanting vehicles that were as near as possible equivalent to internal combustion engine vehicles in terms of their performance. And a lot of people really wrote off LFP and said that they would, have a declining market share. And China started to produce a lot of LFP batteries. And I know people in the West, in the Department of Energy and in some of the national labs, at one point were quite dismissive about the potential growth of LFP and saying, really, this is something that is just for the Chinese market because they're prepared to tolerate inferior performance. But one of the big stories in the battery market in the past couple of years is that BYD, one of the big Chinese battery companies, has developed a concept which they call cell to pack. And the idea is that you engineer all of the weight out of the battery, so you can have, although it's a less efficient cathode material in terms of its ability to store energy, you can cram more into it. You can achieve a higher volumetric density of cathode material for any given battery weight. And so what they've managed to do is use a sort of slightly inferior chemistry, but still attain high levels of performance. And there are other things like the inherent safety of LFP material, why we might like to use it. And so, although in the past perhaps some of the predictions around LFP were a little bit dismissive, we're actually starting to see an uptick in demand and a growth. And people like Tesla have started to use LFP in their sort of standard range, lower priced vehicles. And what they're finding is that consumers are prepared to tolerate the sort of slightly lower performance for the decreased cost in terms of range, and they're finding that a shorter range will satisfy their needs. So we're actually seeing a sort of unexpected growth in the LFP market, and not just, you know, if we look beyond passenger vehicles, and if we think about other applications like energy storage, you know, LFP with its lower energy density is still interesting, because if you're putting shipping containers out in the desert full of batteries, you know, it's cheap space. You don't need the energy density by weight or volume. It's not quite as critical, and so actually it's a good enough technology. So the downside is energy density. The Chinese have started to work their way around it. The market share is contested, but then, you know, let's look at this in terms of the global distribution of resources that are going to be used to produce these batteries. So we can see that in terms of Russia and Ukraine, Ukraine potentially interesting for manganese, for LMO, although and also for NMC. The big story with Russia is largely around nickel, but also around cobalt. And we'll see in the next couple of slides, there's also a potential story around Ukraine and lithium. And so if you look at global cobalt production, the DRC absolutely dominates in terms of global cobalt production. And there's all sorts of concerns with the DRC, why people are looking at you know, ethical sourcing, because there's a lot of cobalt that's produced by artisanal small-scale mining. There's concerns around child labour in the supply chain, and so, you know, there's an understandable squeamishness from automotive manufacturers in the West around where cobalt comes from, and so people understandably are looking to try and diversify that. Now Russia, whilst, you know, relative to the DRC is a small producer of cobalt, they're still significant. They're still the second largest producer globally, and, you know, the cobalt comes as a side product of the large quantities of nickel production that take place in Russia. But we can see that over time, you know, the Congo really dominates in terms of cobalt production at the moment. Now, in terms of the actual flows, once it's come out of the ground in the Congo, it all makes its way to China at the moment, which has got the sort of real centre in terms of the other elements of the supply chain that are able to take that cobalt and valorise it and turn it into you know, battery grade materials. Now, we can see over time, you know, the production of cobalt in Russia has started to grow a little bit in recent years with the extraordinary demand from EV battery makers. You know, everyone around the world is trying to gear up production to try and serve that market. And understandably, Russia's war in Ukraine has started to spook markets, and, you know, people are concerned around future cobalt supplies, and that has really heightened price volatility, and we've seen you know, some extraordinary things on the London Metal Exchange around nickel prices as well. So in terms of nickel and Russia, Norilsk, big producer of nickel, and as we said about cobalt coming from that as a byproduct. When we look at doing life cycle analyses of battery production, when you look at nickel in that, globally, the figures for the environmental impacts of nickel production are skewed by how dirty the processes in the real scar for production. And so to some degree, if Russian nickel doesn't find its way into Western batteries, we might want to reevaluate some of those figures in terms of the environmental impact of nickel production, because other producers do this in a better way. But in terms of, you know, sulfur dioxide, in terms of releases to nature, you know, this massive spillage. Norilsk has been seen as Russia's most polluted city. There's been efforts within Russia to try and you know, clean up Norilsk, but there's still significant environmental impact, and you can see the impact of some of the industrial accidents that have happened in the reels, diesel spillages, and how these have then created enormous environmental problems downstream as a result of production there. Now, lithium is also key. If we sort of just go back up to this graph here, we can see at the moment, South America, you tend to get lithium from brines, where it comes out the ground. In Australia, you've got lithium from hard rock deposits. There's an enormous demand for lithium, and at the moment it's forecast that the current supply chain isn't going to meet that demand, and that there will need to be massive investment in the lithium supply chain, because the forecast demand is expected to grow to 2.4 million tonnes of lithium carbonate equivalent by 2030, and this is going to require 7 billion investment every year for the next sort of 6 years in order to meet that demand. And we sort of passed the milestone last year in terms of global demand for lithium exceeding supply for the first time. And obviously there are additional challenges in terms of the costs around lithium, because there are all sorts of challenges around transport and logistics, which are also adding cost to that. Now, correlation doesn't necessarily equal causation, but it's certainly a factor that people are considering the mineral wealth of Ukraine in the context of this war that's ongoing. And a few days before the announced invasion, there were some scientists from the Ukrainian National Academy of Sciences, and they published results of a study looking at hard rock deposits of lithium, and they were saying that there could be as much as 500,000 tonnes of lithium oxide in the form of various deposits, and that there were Western and Chinese countries, companies that were interested in bidding for exploration permits. And so obviously, this was a fairly new finding in terms of reserves, but this is something where now obviously those plans will be on ice until the situation resolves. And then another story is around sort of phosphate as well, for lithium iron phosphate. Russia and Belarus are big producers of fertilizers, and there are potentially impacts around Russia's war in Ukraine around phosphate supply as well, which is important for lithium iron phosphate batteries, that other chemistry that we were talking about. Now, platinum group metals are going to be really significant in the future in terms of the hydrogen economy. So this is the group of metals, the platinum group metals, and let's look at some of their applications. So at the moment, we see the use of platinum group metals in catalytic converters, and obviously you're going to hear from Johnson Matthey, or you might have said that you've heard from them already, one of the big producers of platinum group metals around the world. At the moment, used in automotive catalysts for ICE engines, but there's going to be a pivot to using these potentially in the future in the hydrogen economy. And so when we look at the sort of future of a hydrogen economy, we can see that there are all sorts of potential future sources of hydrogen, but of course, with the pivot towards clean energy production, we want to see more hydrogen coming from renewables and potentially nuclear. And then obviously you haven't got the emissions at the point of use. And it's about hydrogen is not just going to be used in transportation applications, but a wide range of industrial applications and potentially things like decarbonising steel production. And so at the moment, there are a range of different technologies that are used for producing hydrogen from clean electricity. So people talk about, before we go into the electrolytic production of hydrogen, you get blue hydrogen from hydrocarbons through steam methane reformation and other processes. But then for production of hydrogen with an electrolyser, you need a source of electricity. So people talk about green hydrogen from renewables. They also talk about pink hydrogen from nuclear power linked to an electrolyser. Now, obviously, there are different characteristics in terms of those energy sources and their match to different electrolyser technologies. And we're interested in polymer exchange membrane electrolyzers. They're the ones that use platinum group metals for hydrogen production, but they can deal with variability. So if you want to produce hydrogen from renewables, you need a PEM electrolyzer if you're going to be able to deal with that fluctuating energy input. Whereas for hydrogen from nuclear power, alkaline electrolyzers, which aren't so dependent on critical materials, might be okay because they can deal better with constant supply of electricity. And so we can see here the sort of construction of PEM electrolyzers, which are a bit like a PEM fuel cell that you would find in an electric vehicle, but working in reverse. So they have a proton exchange membrane in the middle with separating the two sides. And then you have a loading of platinum on one side and a loading of iridium on the other. And you can put hydrogen on one, sorry, you put electricity through and it separates the water into hydrogen and oxygen. But iridium's a real challenge, platinum's a real challenge, expensive materials. And iridium is incredibly scarce. There's not a substitute for it in the anodes of PEM electrolyzers. It's got very unique properties. And they've said that, you know, the global demand for iridium in PEM electrolyzers could be equivalent to 470 to 1400% of the current global mining rate. And we can see that when we look at USGS data for platinum group metals, you know, Russia here is a significant producer. And it's a byproduct of platinum mining, so significant dependency on South Africa and Russia. And we can see more recently, you know, increases in the price of iridium and platinum. And for Russia, it's not just about the materials that are used in the production of key technologies for the hydrogen economy, but obviously as a major hydrocarbon producer, they also see an opportunity around the hydrogen future for the production of hydrogen from their hydrocarbons and the export of those to other markets, such as Europe. So I think, you know, there's a combination of factors here, both in terms of hobbling the supply of materials that could be used to build key technologies for the hydrogen economy. And also, you know, Europe faces an energy crisis at the moment as a result of trying to wean itself off of Russian gas, and there's a missed opportunity here around you know, potential cooperation and collaboration around hydrogen here. So electrolyzer technology will depend on how the electricity is generated. Iridium is a real concern for PEM electrolyzers, and demand will outstrip supply. And you know, there's a whole range of supply risks around platinum, but one of the things that we don't quite understand at the moment is what will the transition look like in terms of the tail off of platinum group metal demands from auto catalysts, and then the uptick in demand for platinum group metals for the hydrogen economy. So, you know, moving on to another area where Russia's war in Ukraine is going to have critical material impacts is around semiconductor manufacturing. So, as part of the sanctions against Russia, the US has cut off Russia's supply of microchips, but Russia is responsible for some of the key materials that are used in the production of microchips. Well, should say, in fact, Russia and Ukraine. And it's important to note that, you know, semiconductors aren't just used in high-tech applications like computers and PCs, but also in a lot more mundane applications such as sort of power conversion, which for our pivot to clean energy technologies is particularly important. And so we're in a bit of a perfect storm for the semiconductor industry, because they're already facing lots of different supply chain challenges as a result of the pandemic, and they're trying to recover production to previous levels. And obviously that sort of supply shortage has impacted all sorts of different sectors. You know, the automotive sector is really struggling to produce vehicles, you know, all sorts of challenges around IT procurement at the moment. And one of the problems is, in terms of critical materials, is that Ukraine has been one of the main producers of neon to the level of purity that is required by the semiconductor industry. And the neon was produced as a byproduct of oxygen production for Ukrainian steelworks. And as we often find with critical materials, the challenge is that many of these key materials aren't produced as a main product in their own right. They're produced as a byproduct of producing some other material. And so the noble gases, including neon, but also some others, were a sort of side stream from this mass production of oxygen that was used in the enormous steelworks in Ukraine. And so the economics of that whole process aren't dictated by the neon, they're dictated by the production of the oxygen and the demand for that in steel production. And so there's a real sort of challenge to resolve here, because obviously that production is unlikely to resume for some time, and to try and build that capacity elsewhere would be, you know, ruinously expensive. And also the fact that it would be difficult to build that capacity just for the production of noble gases if you haven't got an attendant use for the bulk oxygen that is being produced as the main product. And it's a real challenge, because just going back to automotive applications here, you know, we can see how with the transition to not only electrification, but also this idea of sort of autonomous mobility and, you know, sort of automated driving, there's ever-growing semiconductor value in a car. And then it's not just about, you know, in terms of the sophisticated computer electronics for all of that intelligence, but it's also about the powertrain and all of the semiconductors that are used in that. So real challenge for the automotive industry if semiconductor supply is constrained. And it's not just about the gases as well. So there's a company in Russia that produces hexafluorobutadiene, which is used as an etchant, and Russia export all of this to foreign companies. And at the time of the development of this plant, in this sort of cluster of plants that produce chemicals around, you know, chlorine, fluorine and bromine, the only other producer in the world was in Italy. And so, you know, you have to wonder what could be the impacts of this war if there are further sanctions, export controls and all the rest of it of this etchant. And at the moment, the main customers are in Japan. So many chip manufacturers have said in the short term, they don't face immediate challenges because they've got a diversity of supply chain for some of these different key precursors. The White House has already told everyone to be on guard, realising that there are potential ramifications. But also there's the sort of, it's not just about how much material is out there and how much is needed and reconciling supply and demand. But if everyone goes into protection mode and tries to panic buy inventories and ensure that they are resilient against supply disruption, then, you know, everyone loses in a way. So it's trying to sort of find a way of balancing individual companies protecting themselves and the market functioning. But there's all sorts of downstream potential, you know, in terms of potential knock-on effects. So another sort of key material that comes out of Russia, it's not necessarily considered a critical material, but it's still something that is of significant concern, is titanium. You know, we know about titanium in aerospace applications and in hip replacements. It's got incredible strength to weight, and it imparts unique properties to the alloys that contain it. And so it's used in aerospace and all manner of different industrial components. And one of the challenges is that, again, Russia is one of the few places that produce titanium. Russia created this whole special economic zone, which they call Titanium Valley, and the world's largest titanium manufacturer, VSMPO VISMA, is located there, and it accounts for 98% of the total Russian production output of titanium. And titanium is considered a critical material by the US, and it imports 95% of the titanium it consumes. And there's been a difference in position between Boeing and Airbus. So Boeing had warned around the tensions in Ukraine, and they've said that it was creating some unfavourable conditions. But when everything kicked off, they took quite a principled stand and said that they weren't going to be purchasing titanium from Russia anymore, although, there's a little bit of complexity to that. By contrast, Airbus in Europe has said to the EU, don't block imports of titanium from Russia, saying that sanctions would be deeply harmful to the European aviation industry, but they wouldn't necessarily harm Russia's economy. Now, I think since I put that bit together, there have actually been some tariffs that have been introduced on certain Russian materials, and I believe that this could have been one of them as well. So the EU is very dependent on a whole range of critical materials from Russia. We've seen palladium from the platinum group metals, vanadium, again in the future for energy applications, may find use in vanadium redox batteries, flow batteries. Phosphate rock, we've seen use of phosphate will be important in LFP, lithium ferrophosphate batteries. Aluminium, again, you know, tons of applications used in batteries, in the anodes, also used in, you know, for lightweighting for vehicles as an alternative for steel. So in some higher end electric vehicles, we see aluminium body structures, which enable vehicles to be lighter and to be more efficient. We also see like enormous growth for nickel in a whole range of different battery applications, and you know, a whole range of other things. So we really, you know, we need to look at addressing some of these key vulnerabilities. And we see that there's going to be a shift, and this graphic came out of the Financial Times, but it draws on JRC data from the EU Joint Research Centre, and they say, you know, in this move from an economy that's reliant on fossil fuels to one where it's reliant on raw materials, there's going to be a shift in terms of the balance of where we source things from and what countries are supplying those different materials. And they're saying, you know, at the moment we're heavily dependent on fossil fuels from Russia, but in the future we're going to be dependent on critical raw materials that are used in the production of a range of different energy devices, and lots of those at the moment. China is the main sort of supply chain bottleneck. But I think, you know, revising this in the context of Russia's war in Ukraine, we can see that actually quite a few of these different materials, there are connections with Russian and Ukrainian supply. And so I think, you know, in conclusion, there's so much competition for a whole range of different materials across a whole range of sectors. And at the moment, because of this inexorable demand, we're scrabbling around the world to look at where we can produce these materials from. And I think for Russia, there's materials that it produces at the moment. There's also enormous potential for production from some of these reserves. But one of the things is that where elements of the Russian economy are underdeveloped, there isn't the value chain to exploit these materials in the way that there is in some other countries. And so, you know, it's a missed opportunity for us as a world, because some of these materials are key to the energy transition, key to our survival as a race, you know, in being able to decarbonise, and yet we're unable to maximise the potential of our global assets as a result of this really nasty, you know, situation with the war in Ukraine. And I think also some of the concern is that as China takes a sort of non-aligned position in terms of the West's response to Russia's war in Ukraine, China stands to potentially be a real beneficiary and reinforce its dominant position, both in terms of, you know, rare earths, in terms of battery materials, and in terms of other materials as well. And so it poses a real difficult challenge for the West as we seek to sort of scale the production of these key technologies. And there are things that we can do to wean ourselves off of certain materials. So in terms of cobalt and nickel, we can look at using those alternative chemistries like LFP. But then again, as we've seen, you know, with Russia also as a producer of phosphate rock, that isn't straightforward either. And I think, you know, for the hydrogen economy, there's less certainty, but there's real challenges around the sourcing of platinum group metals, which largely come from, or where a significant proportion of those come from Russia as well. And so, yeah, lots of challenges, lots of unanswered questions, and lots of unseen connections between different sectors with a lack of supply chain transparency. So it's often hard to see how impacts on raw materials translate to impacts on different elements of the supply chain and on finished product at the end of the day. And I think one thing that is going to be really clear is that Russia's war in Ukraine is going to cause a realignment of different supply chain patterns throughout the global economy. And these are going to be long-lived, they're going to be generational, because once people switch suppliers and start establishing new relationships and new trade routes, you know, they're often hard to unpick. People become established in new patterns. And so this is a real challenge for the West, given Russia's mineral wealth and given the West's already challenging position globally, given China's aggressive approach to secure access to key critical material supply chains. So I hope that's been interesting. Here are my contact details if anyone would like to take those and follow up with anything offline. I should say that there's going to be a blog post about this where I'll set some of this out in a bit more detail that's going to be published in American Affairs, and I can forward the link to that to Marta when that comes out. And yeah, any questions and any discussions?
Okay, thank you, Gavin. Let's give him a round of applause. So we have some time now for questions and discussion with Gavin. Cooper, you look like you have a question. Go ahead.
I do have a question. Thank you so much for your talk. That was incredible, Dr. Harper. I guess something that I'm particularly interested in was at the very beginning of your presentation, you were talking about how the UK was exploring a lot of recycling initiatives for critical materials.
Yeah.
So with the European Union in particular, there's not a lot of critical materials available in the continent. Do you think like it's really important, I guess, for policymakers to, I guess, track the amount of critical materials inflows going into the EU and make policies so that way whatever gets imported into the EU stays there through recycling, so that way in the future maybe you're a little bit less reliant on other countries for those materials?
Yeah, of course. So there's a lot to unpack there, and I think obviously in terms of the presentation I focused much more on supply of materials, but without necessarily then going on to talk about some of the things that we can do to mitigate against those potential supply disruptions. I think in terms of different critical materials and the importance of recycling, depending on what material you look at, there are different opportunities. So if we take, for example, battery materials, the challenge that we've got around EV batteries is that at the moment there aren't a great deal of lithium-ion batteries out there in the economy. There are a few phone batteries, there are some power tools and things sitting in the back of people's drawers, but there isn't the volume in terms of lots of EV batteries coming to the end of life needing recycling. So it's going to take some time for that flow of secondary material to work its way through the economy and to then be able to use that material and put it back into the supply chain. Now, returning to your point around data and around tracking that data, we did a piece in Science around the global implications of the EU battery regulation. So in brief, the EU have set some targets around the future recycled content of EV batteries, and so they're saying, for lithium-ion batteries in the future, we want this % of the lithium, this % of the cobalt, this % of the nickel to be recycled. Now that's great if you can get access to that material. What we're seeing at the moment in the UK, for example, we've got people that are building battery recycling plants. They're not actually building battery recycling plants, they're building plants that will take a battery, that will shred it and will produce black mass by sorting out the copper and the aluminium, and then you just get like the cathode powder that's left. Now that's great, but at the moment we don't have the steps in the UK to join that loop and to be able to valorize that material and do something useful with it, because we just don't have that capacity at the moment. So what's happening? That material is leaching out of the economy and it's being sold back to the Far East because they've got the highly vertically integrated industry to make some use of that. The other challenge, I think, is going to be when you look at the sales of second-hand vehicles. So in the UK, we have our steering wheel on the other side from you, and as a result of that, when those cars get to the end of their life, we can't really sell them anywhere else because no one else wants them because the steering wheel's on the wrong side. So we've got a recycling industry in the UK where those cars get scrapped and recycled in the UK. Now Europe's got a bit more of a challenge because they have their steering wheel on the same side as most of the rest of the world. As soon as cars in Europe get to the end of their life, or there's someone else in a lower tier market that is prepared to buy those cars, fix them up, do the repairs because labour in those countries is cheap. And so there's a ready export market for high mileage, worn out European cars that can then be shipped to a secondary market. Now, if we start doing that with EV batteries, we end up with a load of batteries leaving the EU along with their critical materials, ending up in a market where perhaps they haven't got the capacity to be able to recycle and dispose of those at the end of life properly. And there's all sorts of ethical concerns around that as well. And you've got this critical material leakage then seeping out of the EU into a different market, you know, and then, so if in the EU you're setting targets and saying, well, we need this percentage of recycled material, where are you going to get that material from if it's leached out of your market? So that's the case in terms of batteries. If you look at rare earth magnets, I think that the picture is different because they've been used in a range of different applications for longer than lithium-ion batteries. So there are already sources of urban scrap, you know, that can be mined. There are warehouses full of old PC hard drives that are waiting for disposal, and they need to be done in a secure manner and all the rest of it. But if you put hard drive into a shredder, the magnet sticks to all of the shredder and it gums things up and it acts as a abrasive and ruins your shredder. And so if we could cut those magnets off the corners of all the hard drives, there's a source of neodymium there, and that's what one of our companies, Harper is trying to do. And there, you know, there's demand for rare earth material, but there are already secondary reserves that we could potentially mine. But I think what you're saying, you know, about data, you know, a couple of things sort of, in God we trust, all others bring data, and also the fact that sort of, you know, if you put junk data in, you get junk data out. And at the moment, part of the challenge is like we just don't collect it, we don't have it, we don't know what these flows of critical materials are. We're trying to make estimates within our Metfotech project. We're working with other partners, we're working with people at the British Geological Survey that have just won this contract to be a sort of UK intelligence centre around critical materials. But it's clear from what we're all looking at within our collaboration that we're sort of fighting in the dark at the moment because no one's bothered to collect this stuff. And so to prepare a sort of and mobilise a response to this critical materials challenge is hard when you don't know how much of the stuff is out there, how much is available, etc.
Thank you very much. That was a really, really cool response.
Thank you.
Yeah, it sort of puts me in the mindset too, talking about these hidden connections between different materials in the course of your talk. And I think that's not something that a lot of the fundamental science community has an awareness of, or even, you know, what the fundamental processes are to obtain pure nickel for that matter. So are you aware of any efforts? I mean, it sort of sounds like this is what you're doing to kind of put together that information to highlight current critical materials issues as they relate to sustainability for, you know, the chemical community. So what we'd like to have, for example, is, you know, sort of a primer on this is why rare earths are critical. A lot of people already know that story, but
yeah.
Other stories about, you know, this is why titanium is considered critical for some applications, and what connecting that to the fundamental chemistry so that we can see how the sustainability of the process impacts criticality as a starting point for thinking of ways to improve the sustainability of the fundamental separations process, for example.
Yeah, okay. So I've just dumped into a chat something that may be a useful resource. It's a link to our Policy Commission Securing Technology Critical Metals for Britain, It's really, really accessible, I think, because it was written for politicians, so it had to be. And that focuses on a number of key sectors: battery materials, rare earths, platinum group metals, and aerospace materials, which, you know, you can see they're what we thought were the key materials in the UK, and it explains some of the challenges around that, both on the primary and the secondary side. And there's some good diagrams in there. There's one that came from the APC that shows the whole battery supply chain from raw materials all the way through to finished product. So it's not exactly what you're talking about, but it's sort of a stab in the right direction. It's richly illustrated and it's quite accessible. I think in terms of, I mean, I'm less of an expert on the primary production side than looking at some recycling processes and things on the secondary side. One of the, so what are the sort of key things that I would say from our understanding? I mean, I've looked a lot into recycling of lithium-ion batteries, and I think one of the challenges there in terms of the production of secondary materials from lithium-ion batteries, there's a couple of different analogies. One of them that I use is it's a bit like a game of snakes and ladders, we call it. I think you might call it ladders and chutes, you know, where you sort of start off with the raw material, and each processing step, you know, you're going up a number of squares until you reach the top where you've got your finished battery, your finished article. Now, there are different processes, you know, and like pyrometallurgy takes you a really long way down the board to a much earlier stage. Hydrometallurgy, a little bit less so, and direct recycling, you know, keeps you fairly close to the top of the board. And I think at the moment, a lot of the technologies that people are using for recycling box you into having to come a long way down the board, because the way that everyone deals with variety at the moment is by shredding things. And the challenge with shredding things is then you've got everything mixed up together, and you have to put a lot of energy then into the chemical separation, because you need processes that are so much more selective than if you were able to keep things segregated from the off. And the other thing that we say is it's like a bit like a cake and a blender. Like if you had a Victoria sponge, cake, jam, cream, cake, and you wanted to separate that into separate components, you'd probably try and sort of pull the sponge apart and scrape off the cream and scrape off the jam and keep that all in separate boxes. But that's not what the recycling industry does at the moment. It sticks the cake in a blender and then looks at the blended slurry and then tries to work out how to pick out all of the bits. So I think, you know, we talk about the waste management hierarchy, you know, and sort of, you know, reduce, reuse, recycle, recover, and then finally disposal. But within recycling, there's a whole blend of different technologies, from sort of more preferable to less preferable. And at the moment, because this industry is in its genesis, some of our critical materials recycling technologies are at this sort of base level of fairly crude methods and things that have been repurposed from sorting general wee or whatever, you know, and they only recover high value materials, the sort of heavier metals and stuff that's easy to get out of a pyro process. Whereas actually, if we really want to move towards a circular economy, we want to recover more of the value, more of the materials, and things like the lithium as well, which would end up in a slag if you put it in a pyro process. Whereas if we could keep things in a higher value state through direct recycling, then we can recover not only more of the material, but also more of the value that's embedded in that material, from transforming it from mined material all the way up to sort of final material. And I think that's the way we want to try as far as possible to retain value in the West once we've imported it and once we've, you know, sort of sourced it from elsewhere. And I think, yeah, we've got to go on a journey there.
Thank you. We have some time for more questions if there are some from the group.
I wondered if you had any thoughts on whether the technologies might adjust and to maybe simplify things a little bit. And I don't quite know how to say that, what I'm trying to say, but, you know, I think a lot of the argument is that in order to have these electric vehicles and to have these navigation systems and to have these microchips and blah, 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 all of these things require critical metals. And, you know, for example, cars did in fact exist that did not have navigation systems. There are in fact, you don't have to have the little display screen in your car for it to get you from point A to point B, right? So I just wondered if there were aspects of design that you were seeing maybe in the automotive industry or beyond, that maybe was seeking to simplify some of the products that they're putting out so that they can still sell product, right, to affect the bottom line, but maybe take down a notch their need for some of the critical metals. Like, are you seeing the industry responding in any way in that direction?
No, but
Okay.
it could. So I think in terms of simplification, so some of the things that you're saying, I think there's an enormous amount that could be done on the design of things like battery packs to simplify not just end of life treatment, but also reuse and remanufacture. So at the moment, for example, if you've got a wiring loom within a battery pack, it's flexible, it's a snake that connects things up, and you can get an operative that plugs all of that in the factory. But when it comes to the end of life, if you want to remove that in an automated way, that battery's been driving around for however many 100,000 miles, it's not going to be in the same position. Everything moves about. And so you can't tell a robot to pick that up from there because it could be over there or it could be over there. And so things like using rigid buzz bars, so it's always in the same place. There's a set of screws and the robot knows where to go to get those screws. Module to pack, sorry, cell to pack. So this concept by BYD, if you think about a Tesla battery, you've got 8,000 little 18650 cells, less in some of the newer ones because they're bigger. And then they're combined into modules, and the modules in turn are combined into a battery pack. And you've got like lots of different challenges at each stage of disaggregation, from taking the pack out of the car, taking the pack to bits, taking the modules to bits, and then dealing with the cells that are all these little tiny Swiss roll cylinders. And I think if you look at that and you compare that to, say, the BYD battery, and I think some of the reason why China's getting it right is because of the vertical integration. You've got companies that are producing the materials, producing the battery, producing the car, and they can also see that they're going to have to recycle that battery at the end of life and put that back into the system. So this high degree of integration, although they're not billing it as a designed for recycled battery, I think that thinking's gone into it. And there you just have big flat cells, and the cells are part of the structure, and you can change them about, and the cells combine into the pack directly, and you just emit so many layers of complexity in terms of the structure and the interconnection. And what that means is at the end of life, you can take the cells out, you can change them around, you can, build them into a new pack, take the good ones and make them into something that goes into another application. You can then recycle them easily because they're big and flat. So with a cylindrical cell, it's all coiled up. You just hard to unravel it or separate it. You just feed it into a shredder. Whereas with a big flat pack, potentially you could delaminate those cells bit by bit. That's another presentation which I also have. I'll dump you a link to a conference presentation that I gave recently in Sydney, which is all about battery recycling, if that interests anyone. So that's about simplification in terms of design for recycling. I think there's also a need for simplification in terms of variety reduction. So everyone is doing their own thing at the moment, and people have got competitive advantage through small incremental wins and doing things differently. But the challenge at the end of life is that there's just no similarity. Everyone's got their own proprietary battery standard, nothing fits together. You've got a lack of competition because no one can come into that market and offer a sort of OEM battery, do you know what I mean, or a battery to compete with the OEM. You haven't got like a Duracell electric car battery that you can swap for your Tesla battery in the event that it fails, And I think so if we had more simplification, more standardization, then that would be really healthy. And I think some of that will naturally come as a result of the fact that EV battery technology is expensive and the development costs are expensive, and we see automotive firms merging. So, Volkswagen, Seat, Audi, Skoda, Bentley, Porsche are all the same company now. So there's going to be some commonality with their designs that they put into different vehicles. So simplification on that front as well would be good. In terms of actual vehicle systems, I'm not sure, because I think even if critical materials are expensive, people still will always prize the value and the utility that those materials provide. And yeah, okay, we had cars without sat-nav and you can use your phone and all the rest of it, but I think perhaps it's the wrong way to look at it. Perhaps so there's a couple of different things. First of all, there's, can we produce vehicles that are the right scale for the actual purpose? And you know, most of the time vehicles are transporting a couple of people tops. Do you know what I mean? Most journeys are sort of one-person journeys, and so do we really need enormous cars that are designed for moving a wardrobe, 5 kids, and do you know what I mean, whatever? Probably not for a lot of journeys. And I mean, in China, I think they're getting this right, because they've got this idea of neighborhood electric vehicles, small vehicles that Americans would laugh at, you know, that just do little journeys to the shops and are just like 1 or 2 people vehicles. But actually, for the utility and for the function, that's what you need. But it's, you know, it's a societal shift and it's a change. I think also better utilisation of critical materials through things. I mean, Uber, great example. You know, you've got the one car, but it's serving so much more utility through servicing lots of individual people and their needs and their journeys. Because let's face it, like most of the time, your car is stuck on the drive or stuck in your, you know, sort of parking lot and all the rest of it. You know, just before the pandemic, my old car went wrong, and I thought to myself, do you know what, I'm in the car all the time, I'm going to treat myself to a really nice car. So I went to got a really nice car, stuck it on the drive, and then the pandemic happened and it had been stuck there for sort of 18 months when we weren't allowed to go anywhere or drive anywhere. And that's like really bad materials utilisation with all of that sort of money, investment, materials and all the rest of it. But you know, that's an extreme example. In everyday life, we've still got materials tied up in parking lots that aren't doing anything. Whereas actually, if we could move to product service systems, if we could go on an app and just say, okay, I need to get from A to B, and that autonomous or, you know, assisted vehicle, pay a little bit more for the service, but don't have that money, and by implication, that critical materials resource tied up in something that only one person is occasionally using. So I think that's probably the route, rather than compromising on function. And I'll post that link if you're interested. I will post the link to a recycling talk in the chat, and then people can look at that as well.
Great, thank you so much. Yeah, thanks for sharing these resources with us.
Not at all. You're very welcome, and it's been an interesting conversation, and I hope that there's more touch points in the future, you know, where there's potential for collaboration or you know, working together. Please reach out, anyone, if there's anything that I've said that interests you or anything you'd like to take further, and I will follow up with Martha and send details of this article as and when it comes out.
Great, thank you. Well, please join me in thanking Gavin for a wonderful talk and discussion again.